New bacterial concrete to repair cracks through self-healing technique. Abstract: cracks in concrete are unpreventable and it is intrinsic weakness of concrete. Through these cracks water and salts can seep. It initiates corrosion, further reducing the life of concrete. So there was a requirement to develop an intrinsic biomaterial, a self-repairing technique which can repair the cracks and fissures developed in concrete. This technique is highly desirable because the activity of crack remediation is eco-friendly and natural. The paper discusses the plugging of artificial cracks in cement concrete using Bacillus megaterium. The effect on compressive strength, water absorption, and water permeability of cement concrete cubes due to mixing of bacteria is also discussed in this paper. It was found that the use of Escherichia coli improves the compressive strength and stiffness of concrete. The effect on compressive strength, water absorption, and water permeability of cement concrete cubes due to mixing of bacteria is also discussed in this paper. It was found that the use of Escherichia coli improves the compressive strength and stiffness of concrete. It also shows that there is reduction in water absorption and water permeability when compared to conventional concrete. The bacteria which are going to be introduced in concrete should have the properties of alkali resistance, and it also should form endospore, so that it can withstand the stresses produced in concrete while mixing, handling, and transporting. Keywords: compressive strength, bioconcrete, water permeability, water absorption, Escherichia coli. 1. Introduction. It is generally accepted that the service life of the concrete structures is reduced by the development of micro-cracks, which allows the ingress of water, carbon dioxide, and chlorine ions into the structures. This can cause degradation of concrete and corrosion of reinforcements, resulting in the needs of regular and costly repairs and maintenance works. Cracking in conventional reinforced concrete is virtually unavoided because of thermal effects, early age shrinkage, mechanical loading, freezing and thawing, or combination of these factors. In addition to the associated costs, repairs increase the carbon footprints of the structures and expose them responsible for carrying them out to unnecessary levels of risks. This project aimed to develop a self-healing concrete to reduce the repair and maintenance requirements of concrete structures. 2. Materials and methods. Materials. 1. Portland pozzolana cement, 30 grade. 2. Graded fine aggregates. 3. Graded coarse aggregates. 4. Water. 5. Bacteria equals Escherichia coli. Methods. 1. Mix design of M25. 2. Testing of materials. 3. Working test. 4. Identification of bacteria. 5. Preparation of bacteria. 6. Mixing and compacting. 7. Curing. 8. Implementation and testing. 9. Results. Escherichia coli. Escherichia coli is an obligate aerobe bacterium used as a larvicide for mosquitoes control. It forms spherical endpore. Bacillus spherical is a gram-positive bacteria with rod-shaped cells that forms chains, medium-sized, smooth colonies with an entire margin and also rod. Ability of bacterial concrete to repair cracks. Both attention will be given on closure of cracks and on regaining mechanical properties. Cracks in concrete specimens subjected to various loading situations will be investigated before and after healing. For this, impregnation techniques and scanning electron microscope will be applied. On the other hand, the microorganisms such as cyanobacteria, algae, lichens, yeast, fungi, and mosses etc., which are omnipresent and omnipotent, are responsible for metabolism action that results in microbial deposition of calcium carbonate layer. Also, the process results in re-establishment of cohesion between particles of mineral binding materials and protects against further decay of stone materials. To prove the positive effects of microbial CaCO3 precipitation. The increase in porosity of concrete leads to increase in capillary water uptake, increase in gas permeability along with higher carbonation rate, high chloride migration and freeze-thaw damage. Hand mixing. Hand mixing is practiced for small-scale concrete work. Hand mixing should be done over an impervious concrete or brick floor of sufficiently large size to take 1 bag of cement. Spread out the measured quantity of coarse aggregates and fine aggregates in alternate layers. Pour the cement on top of it and mix them dry by shovel, turning mixture over and over again until uniformity of color is achieved. This uniform mixture is spread out in a thickness of about 20 centimeters. This operation is continued till such a good time a good, homogeneous and uniform concrete is achieved. It is of particular importance to see that the water is not poured but only sprinkled. Water in a small quantity should be added towards the end of the mixing to get the just required consistency. At the stage even a small quantity of water makes difference. After that bacteria medium is sprayed over concrete mixture. Placing. It is not enough that a concrete mix correctly designed batched mixed. It is of utmost importance that the concrete must be placed in systematic manner to yield optimum results. The precautions to be taken and methods adopted while placing concrete in the molds. Hand compaction. Hand compaction of concrete is adopted in case of small concrete works. Sometimes this method is also applied in such situation where a large quantity of reinforcement is used which cannot be normally compacted by mechanical means. Hand compaction consists of rodding, ramming and tamping. When hand compaction is adopted, the consistency of concrete is maintained at high level. Tamping is one of the usual methods adopted in compacting roof or floor slab or road pavements where the thickness of concrete is comparatively less, and surface floor slab or road pavements where the thickness of concrete is comparatively less and surface to be finished smooth and level. Curing. Concrete derives its strength by the hydration of cement particles. The hydration of cement is not a momentary action but a process continuing for a long time. Curing can also be described as keeping the concrete moist and warm enough so that hydration of cement can continue. More elaborately, it can be described as the process of maintaining a satisfactory moisture content and a favorable temperature in concrete during the period immediately following placement, so that the hydration of cement may continue until the desired properties are developed to a sufficient degree to meet the requirement of service. The casted cubes and cylinders are immersed in water for 3 days, 7 days, 14 days, and 28 days. Workability of concrete. Workability is the amount of useful internal required to produce full compaction of concrete. It depends on I. Grading of coarse and fine aggregates. 2. Quantity of cement paste. 3. Consistency of cement paste. 4. Type of aggregates. Slump test. Slump test is most commonly used method of measuring consistency of concrete which can be employed either in laboratory or at site of work. It is not a very suitable method for very wet or very dry concrete. It is used conventionally as a control test and gives an indication of the uniformity of concrete from batch to batch. The deformation shows the characteristic of concrete with respect for segregation. The thickness of metallic sheet for the mold should not be thinner than 1.6 mm. For tampering the concrete, a steel tamping rod 16 mm diameter, 0.6 meter along with bullet end is used. The mold is then filled in 4 layers, each approximately 1/4 rth of the mold. Each layer is tampered 25 times by the tamping rod, taking care to distribute the stroke evenly over the cross section. After the top layer has been rodded, the concrete is struck off level with a trowel and tamping rod. The mold is removed from the concrete immediately by rising it slowly and carefully in a vertical direction. This allows the concrete to subside. This subside is referred as slump of concrete. The value of slump equals 85 mm. 3. Experimental study. The materials used like cement, coarse aggregates, and fine aggregates are shown below. The properties of constituents are also presented in the table. 4. Results and discussions. A. Compressive strength. The concrete was tested for 7 days, 14 days, and 28 days. Of curing. It was loaded in compression testing machine. Cubes of size 15 15 15 was used. Compressive strength equals ultimate load / area of specimen equals P/A, where P equals ultimate load, A equals area of specimen. The comparison between compressive strength of bacterial concrete and conventional concrete is tabulated as below. B. Tensile strength. It is indirect way of finding tensile strength of concrete. After 7 days, 14 days, and 28 days of curing, the specimen were placed in CTM by placing horizontal. Tensile strength equals 2p/3.14 dl, where d equals 15 cm, l equals 30 cm. The difference between the tensile strength of conventional and self-healing concrete is shown below in the tables. Conclusions. Introducing the bacteria E. coli into the concrete improves the properties and characteristics of concrete. Experimental investigations were conducted to determine compressive strength, split tensile strength of conventional and bioconcrete. Based on the test results, it was observed that addition of bacteria gives better result. It was observed that both tensile and compressive strength of concrete increases due to addition of bacteria. It was also inferred that increase in both compressive and tensile strength was maximum when curing period was 7 days. Bacteria repair the cracks by producing calcium carbonate, which blocks the cracks and repair it. It was proved that self-healing concrete is better than conventional concrete because of its eco-friendly nature, self-healing nature and convenience to use. Hence we can use bacterial concrete at the place of conventional concrete in structures to get more strength and durability.